Welcome to the 26th lecture in this series. In this lecture, we are going to cover a new data structure, graph ADT. This new data structure falls under the category of nonlinear data structures. Hope you may be remembering that in the last classes we were discussing about yet another nonlinear data structure, which is trees. I hope by this time you remember what we learnt about nonlinear data structure. In a nonlinear data structure, elements are not stored sequentially, rather they are stored in some hierarchical fashion. With this particular presentation, we are going to learn about some of the terminologies associated with graph data structure and what are all the representations that are supported for storing elements in this graph data structure. We now enter into the lecture. As you all know, graph is a nonlinear data structure. We usually denote graph as a set of vertices and edges. So, whenever we represent graphs, we will be having a set of vertices which will be denoted as V, the vertex set, and we will have another set, namely E, which is the edge set. As you see here, a graph would normally look like this. Here you could see that the circles 1, 2 and 3, they all, that is what we call as vertex or vertices, and the lines that connect those vertices, we call them as edges. So, here we call this kind of graph as an undirected graph, just because the edges between the vertices do not have any arrows that indicate the direction of flow, and so we call this kind of graph as an undirected graph. On the other hand, in the figure that you see at the bottom, here you could see the same graph where you could see that the edges between the vertices have some arrowheads that refer to the direction of flow, and so we call this kind of graph as a directed graph. And normally for representing a graph, we usually follow two kinds of representation as we did for other data structures. One is a sequential representation using arrays and another one is a linked representation. The sequential representation using arrays, here it is going to be a multidimensional array, and so we say it as a matrix. So, the matrix will be just telling us the set of edges or links between the set of vertices, and so we call it as an adjacency matrix here, and the linked representation we call it as an adjacency list. Of course, we will see with example how to go for a adjacency list representation and matrix representation in later part of this lecture. And in one of the other lectures, we will be touching upon the two search or traversals associated with this graph data structure. So, as I said before, graph is denoted by G, that includes a set of vertices and set of edges. And we learnt what a directed graph is. In a directed graph, all the edges will have directions dictated by arrowheads, as you see here, and in case of undirected graph, edges will be undirected, there will not be any directions. So, when you make a count of or when we say the flow of information between a pair of vertices, we in an undirected graph we always say that there is flow from A to E and also flow from E to A. And in some graphs, the edges will have some labels, and in the labels may be just labels, or in some other cases it may denote the cost or the weight associated with an edge. In such cases, the graph will be called as a labeled graph, and that labeled graph can even be either directed or undirected. So, here we have a very basic example for graphs. As such, by observing this graph, as you see arrowheads here, you will be knowing that it is a directed graph. Be it a directed or undirected graph, we normally mention or specify a graph as a pair of as a set of vertices and a set of edges, and every edge will be a pair, will be denoted as a pair. That pair indicates the pair of vertices between which the edge actually flows. So, here for instance, if I say that V1 comma V2, then it means that there is an edge between vertices V1 and V2. So, here in this graph you could see that if I have to represent this graph using the standard notation, then I should include two sets. One set is capital V and another set is capital E, where vertex set will have the set of vertices from A to F, and edge set will denote the set of edges, where every edge would be between any pair of vertices. Just because this is a directed graph, here we have AB as one of members of this edge set, but we do not have BA just because the edge here has a direction associated with it. Whereas in case of undirected graph, we will be including both, that is AB and BA. And these are some of the examples for graphs. So, a graph as such, it is a very useful data structure. It finds application in many domains. For instance, for representing molecular structure, we may make use of a graph, and not only that, in computer network we do make use of graph to denote the nodes that are associated with the network. You know, a network is a collection of nodes. So, those nodes can be represented the way we represent a vertex in a graph, and the lines between them actually denote the interconnection between those nodes within a network. And apart from that, we can have many more areas where graphs are actually employed, say in electrical and other communication networks, for dictating airline routes in a flow chart, and for planning purposes, in order to dictate the flow, you can make use of graphs. So, this slide is just to tell you the basic difference between what a directed and undirected graph is. As you know, by this time, in a directed graph, edges will have directions associated with it. So, here there is an edge from V1 to V2, and there is one edge from V2 to V1, right. So, here we actually say that they are two different edges, and their direction actually dictates the meaning, like from where the information or the data flows. On the other hand, in an undirected graph, we will be just mentioning the pair of vertices just if there is an edge between them. And so, in this case, for instance, there is an edge between two vertices, say V1 and V2, and if you want to make a note of the edge set of this particular pair of vertices, in that it will include both V1 and V2, which is equivalent to V2 comma V1. And there are some other terminologies associated with graph. One is adjacency. So, we say that two vertices are adjacent to each other provided they have an edge between them, or in other words, we can say that if there is an edge u comma v in a graph, and we say that the edge E is incident with vertex u and vertex v. So, because they are the endpoints between which the edge actually occurs, and so we say that this should be true for two vertices to be adjacent, which actually means that there should be an edge between them. And in some undirected graphs, we can also notice self loops. So, what we mean a self loop is that there will be an edge that starts from a vertex and ends in the same vertex. So, we call that as a self loop. So, in this case, you could see that the endpoints are two different vertices, but for a self loop in a graph, those two vertices will be one and the same. And the next terminology is the degree of a vertex, and the degree of a vertex is usually the number of edges incident on it. If we consider a vertex, that many number of edges that are incident on it counts for its degree. And in case of a self loop, it is counted twice. As I said, it has one edge leaving out from the vertex and another edge entering into the vertex. So, we normally count a self loop twice. In order to denote the degree of a vertex, we use the term degree of V. And so, here we have an example graph. It is an undirected graph. By looking at the edges, we can say, as there are no edges or arrowheads, as there are no arrowheads in the edges, we can come to know that it is an undirected graph. So, here when we count the degree for this vertex D, you could see that there are 3 lines leaving out of it, or we can say that 3 lines entering into it, and so this particular nodes or vertex degree is 3. and we have one isolated node or vertex in this particular graph whose degree is 0 just because it does not have any edge entering or leaving it. And we have a self loop here for the vertex C. You could see that the edge starts from C and ends in C, and so we call this as a self loop. Now, there are certain terms associated for a directed graph. One is adjacent. So, it is much similar to what we saw with undirected graph. So, we call a vertex u as adjacent to another vertex v in a directed graph, provided there is an edge between those two vertices u and v, such that vertex u is the initial vertex and vertex v is the ending or terminating vertex. So, here we need to be careful about the terms. It is adjacent to. Whenever we say that it is adjacent to, we are supposed to mention the start vertex, and we have another term called adjacent from. So, whenever we say adjacent from, it means we are mentioning about the terminal vertex or the end vertex. So, we say that vertex v is adjacent from u, where u is the starting vertex and v is the terminal or end vertex. And in case of directed graph, degree is not 1, it is 2. So, we talk of in degree and out degree. Whatever edges flow into a vertex, we call it as in degree. It will be counting that edge for in degree, and if an edge starts from a particular vertex, then we count that particular edge in its out degree. So, as such, the definition for in degree is the number of edges with vertex as the terminal vertex, and out degree is the number of edges for which this vertex is the initial vertex. Accordingly, we count for in degree and out degree. So, here let us have the another example of a directed graph. So, here say let us consider the vertex D. So, here you could see that there is one edge flowing out of this vertex and two edges flowing into this vertex. So, here for this edge D is the initial vertex, and so its out degree is 1, and for these two edges D is the terminal vertex, and so we say that its in degree is 2. And when we consider the other vertex F, as you know, it is an isolated vertex, which means there are no edges flowing into it or coming out of it, and so its in degree and out degree both are 0. And as you have a self loop here, so with this self loop what we say is that we say that B is adjacent to C and C is adjacent from B. Next is the terminology called a path, a simple path, a path length and a cycle. So, path is nothing but it refers to a sequence of vertices, and a path actually accounts for a set of edges between those two set of vertices. So, as we say, for instance, if I want to determine the path from A to C, then I may take A E C, or I can take A D C, or I can have A B D C or A B C. So, all those sequence of vertices that help me to reach C from A, those things will be called as path. If in case these edges are all associated with some labels or weights, then we may have to count up those weights to determine the length or cost of that path. So, that is what we say as path length. If the graph is an unlabeled graph, then we will be counting the number of edges in that path in order to calculate the path length. For instance, for A to C, if we take this path, then the cost is 2 or the path length is 2. Alternatively, there is another definition called as a simple path. A simple path is one in which every vertex appears exactly once. So, I told you that whenever we specify a path, we will have a sequence of vertices, but in those sequence of vertices every vertex should appear exactly once. If so, we call it as a simple path. And we have a term called cycle. A cycle is actually a path in which the start vertex and the end vertex are one and the same. Like, say for instance, as a path I have a sequence of vertices. If in that path the start vertex as well as the last vertex in the path are one and the same, then we call that as a cycle. So, here we have one more example to understand what a path and what a simple path is. Say for instance, you know what a path is. It is a sequence of nodes or vertices that are all connected by edges. Say here in this case with this graph, V2, V3, V4, V2, V1, we can call that as a path. And so, here you could see in this particular path the vertex V2 appears twice. So, for a path a vertex can appear twice, but for a simple path a vertex should appear exactly once. So, as an example, V2, V3, V4, V5 can be called as a simple path, just because you could see that every vertex appears exactly once. And similarly, we have terms called cycle and simple cycle. As you know, cycle means we have a path that ends and starts at the same node or a vertex. In case of a simple cycle, it should be a cycle where every node appears at most once except for the first and the last nodes. So, in case of a cycle, other than the start and the end vertices to be one and the same, in between also we may have the same vertex appearing more than once, whereas in case of simple cycle only the start and the end vertices in the path can be one and the same, while all other vertices should appear exactly once. Now, we move on to the representation of graphs. As I said, we have two representations like any other data structure. One is a linked representation and another one is a sequential or list based representation. So, the linked representation we call it as adjacency list. The sequential representation, here instead of an array we go for multidimensional array, just because we want to capture the edges that flow between any pair of vertices. So, we go for a matrix to represent pair of vertices, and we call that representation as adjacency matrix representation. So, if we are to implement a list based representation for graphs, then the complexity would be number of vertices plus number of edges, because here we will be maintaining a linked list for every vertex we have on a graph, and whatever edges that originate from a graph we will have nodes in that particular list. So, for instance, I have 5 vertices on a graph, then I will be having 5 different linked lists, and for instance I can take up the first linked list. So, the first linked list would just picture up the edges that are originating up from that particular vertex. So, for every vertex that are associated with that first vertex, we will be having nodes in that particular or the first linked list. That is what we mean as adjacency list representation, and we normally go for this adjacency list representation only if the graph is a sparse graph. So, here in this case adjacency of u contains all vertices such that there is an edge u comma v and that edge belongs to the edge set of this graph. We can also make use of adjacency list for storing a weighted graph. In that case, the weight associated with every edge should also be stored in that linked list, probably in its data part. And the only drawback we have with adjacency list representation is that we cannot quickly determine whether a particular edge is present in a graph or not. It is a bit complicated than adjacency matrix. And the next step for representing graphs is adjacency matrix representation. Here the complexity is order of vertices square. So, as I said, we are going to capture the edges between every pair of vertices, and so we represent this in the form of a matrix, and so it is vertex square complexity. And this adjacency matrix representation is normally preferred when the graph is a dense graph, and for an undirected graph this adjacency matrix will be usually symmetrical, and for a weighted graph we can make use of this adjacency matrix, and instead of storing a value of 1 in this matrix for a unweighted graph, for a weighted graph we will be storing the weights associated with the particular edge in the UV entry in our adjacency matrix. And the advantage of having this adjacency matrix representation is that we can easily determine whether a particular edge is present in the graph or not. So, here we see an example of how that adjacency matrix representation of a graph would look like. You have a graph, it is an undirected graph. So, this is how we fill up entries in this adjacency matrix. If there is an edge v comma if there is an edge E between a pair of vertices v comma w, then we will be marking that with the value of 1, and all other entries will have a value of 0. So, wherever you find an edge, only between those pair of vertices we will put up a value of 1, in all other places the value will be 0. So, accordingly we have filled up ones and zeros in this matrix, and let us consider one example. So, here there is an edge between A and B, just that it is an undirected graph. This edge can be treated as an edge between A and B as well as an edge between B and A, and so you have two ones here. From A to B there is 1, from B to A there is also 1. Likewise, we have populated values for this particular matrix following this rule. So, this is an adjacency matrix for a directed graph. So, here we have an graph which is directed. So, here we consider an edge between A and B. So, here the edge starts from A and ends at B. So, you should put a value of 1 between A and B and not from B and A. So, this will not hold here just because this is a directed graph. So, this is the rule we follow. It is much same, but we consider the direction of the edge as well when we put up values in this adjacency matrix. So, this is an adjacency list representation or a linked list representation of a graph. So, here we have an undirected graph. This graph contains 6 vertices. So, we have some 6 lists A to F, and every list will have nodes associated with it, which actually correspond to edges that originate from that particular vertex. So, here there is an edge from A to B and D. So, the particular list have 2 other nodes which are B and D, and between them, in order to represent a relationship, we have put up links in this. So, likewise we have done for all other vertices, and as such the last vertex F, it is an isolated vertex, and so this list is empty, its associated list is empty. So, when we look at the space complexity for adjacency matrix representation, it is V square, whereas here for space complexity, you know, we may have to create that many lists for that many vertices that are part of that graph, and here it is plus 2 into B of E, because it is an undirected graph, and so every vertex has to be I mean every edge between the pair of vertices has to be represented twice, and so we say it is 2 into B of E. Say for instance, if we consider this edge A to B, so this vertex B will be appearing in the linked list for A, and vertex A will be appearing in the linked list for B, and vice versa. And now we look at the adjacency list for a digraph. So, it is a directed graph. So, here everything is one and the same, except that the direction of the edges matters. So, here A is called the source node and E is called as the sink node, and so we call it a source and sink because there is no other edge after E. So, everything comes to an end at E, and so and you could see that the flow starts from A, and so we call A as the source and E as the sink in this particular graph, and F is an isolated vertex, so it does not come into picture. Other than that, the representation is simple and it is more or less same as the previous that we saw, but you could see the number of nodes is less in this particular list just because every edge is counted once. So, we have the space complexity as A into V plus B into E, where E corresponds to edges. So, to summarize what we have seen so far, we have seen what a graph data structure is. It is usually represented as a collection of vertices and edges. We always denote vertex as V and edges as E. Alternatively, vertices can be called as nodes and edges can be called as arcs. In some other books, people may even use the term nodes and arcs. And we learned the difference between directed graph and undirected graph. In a directed graph, the edges will have direction that dictates the direction of flow, whereas in case of undirected graph, edges will not have any direction. So, we assume that if there is an edge between A and B, we assume that the flow can be between A and B and B and A. And in case of weighted graph, edges will have some weight or cost associated with it. And in an unweighted graph, all the edges are assumed to be having the same weight, or we can say that there are no weights assigned to those edges. And we call two vertices as adjacent provided there is an edge between them. And we learned the definition for degree of a vertex. So, degree of a vertex is nothing but the number of edges associated with a particular vertex. And if it is a directed graph, we call degree as in degree and out degree. Whatever edges that enter into a graph, we call it as its in degree, and that many number of edges that originate out from a graph, a particular vertex, we call that, we count that many edges and call it as its out degree. And then we learned two representations for graph. One is a matrix representation, which is actually a sequential or array based representation. Here it is a two dimensional array that tells us how vertices are all connected. And in case of adjacency list representation, we are going to use a linked list, or in other words we can say it is a dictionary, where we have number of linked lists corresponding to number of vertices, and every linked list will again have set of nodes that correspond to edges associated with that particular vertex. Having learnt a few terminologies associated with graph, now we will have some questions to test our understanding of the concepts that we have learnt so far. So, first question is, what is the difference between a tree and a graph? Can every tree be considered a graph, or can every graph be a tree? And we have already learnt what a tree data structure is. It is a set of nodes. So, in that case, every tree can be called as a graph, whereas in a graph we learned that there is a possibility of having a cycle where we will start from a vertex and end in the same vertex. So, such thing is not allowed for a tree, and so we can generally say that every tree is a graph, but not every graph is a tree. So, if a graph is without a cycle, then we can call that to be a tree. Next is, why is an adjacency matrix inefficient for representing sparse graphs? So, sparse in that sense, the connectivity between vertices is minimum. So, here the complexity is order of v square when we go for adjacency matrix representation. So, in that particular matrix, if the connectivity between the vertices is less, then most of that matrix entry in that matrix will have a value of 0, and so we say that normally for a sparse graph, adjacency matrix representation is inefficient. And why do we prefer adjacency list over matrices for real world large networks? And here the reason is that adjacency lists are usually preferred because for large networks maintaining matrix would be highly inefficient, and so we go for adjacency list representation when we go for real world purposes. So, with this particular lecture, we have covered up only few of the terminologies associated with graphs. We are yet to study some more terminologies of graphs with the next lecture. Thank you.